Okay, last week we talked about the transition to turbulence, and we talked about Reynolds' study in the 1800s that determined that the pipe velocity, the pipe diameter, and the fluid density and viscosity determined the transition between laminar and turbulent states. What I want to do today is just go through a little bit more formally the delineation of dimensionless groups and simply point out that velocity, which has units of length per time, diameter, which has units of length, the density, which has units of mass per length cubed, and then the viscosity, which in absolute viscosity has units of mass per length time, can then be combined into the dimensionless group known as the Reynolds number, which is density times velocity times diameter divided by mu. And if you take each of these units and substitute them in here, you can see that this in fact is dimensionless quantity, the Reynolds number. So the Reynolds number, which is fundamental to many aspects of fluid flow, but in this case talking about the transition from laminar to turbulent flow, is a very common dimensionless group that involves a velocity scale, a length scale, and a couple fluid characteristics. Notice if we had said instead of rho and mu, they each depend on the mass. And so they're the only groups here that are functions of mass. So they always have to appear in a ratio with one another. So we could have defined nu to be the ratio of mu and rho. That's the absolute viscosity divided by density, and that's the kinematic viscosity. The units on nu is length squared per time. So because when we look at these units on the left here, for density and viscosity, the only two variables that involve mass are these two. To create any dimensionless group, they have to appear as a ratio. So we could just as well replace them with the kinematic viscosity. And so then we would have that the transition is a function of velocity, diameter, and the viscosity nu. In this case, we would have found that the Reynolds number is velocity times length divided by viscosity. And again, that's a dimensionless group. It's exactly the same as the one above, but now using the kinematic viscosity instead of mu over rho. Now, how do we know when we have enough groups? This is the basis of the Buckingham pi theorem. And the Buckingham pi theorem states that given a list of, so Buckingham pi theorem says, given k variables with m units, that is length, time, mass, then we require k minus m groups to describe the system. In the first case, v, d, rho, mu, k equals 4, m, let's count the units up here. The number of units, we have length, time, and mass. So we have 3 units. So m equals 3. So k equals 4, m equals 3, which means we need 1 group. How does that change with the second approach where we use the kinematic viscosity? When we use the kinematic viscosity, going over here to the right, we have v, d, and the viscosity, which means k equals 3. But now, velocity has length per time, diameter has length, kinematic viscosity has just length and time. So now m equals 2. Only 2 different units are used. So Buckingham pi theorem in this case tells us we need 1 group. So again, the Reynolds number is sufficient to describe it. So this week after spring break now we're going to be exploring the Buckingham pi theorem in a lot more detail and think about how it prepares us for designing experiments, scaling results, and so on.